But for the first speaker, we have Steffen Schultze. He is a postdoc at the Max Planck Institute, and he will be talking to us about his work on X-ray scattering images. So the floor is all yours, Steffen.
I cannot share my screen yet.
I will give you access in 1 second.
Can you share now? No?
No, I can. Thank you.
Oh, can.
Okay, I hope you can see this. Yeah.
Yeah.
Okay, yeah. So I'm going to talk about my work on Bayesian structure determination from single molecule X-ray scattering. Hang on. So, and we have just heard about the crystallography. I introduce this usually as crystallography without the crystal, so just scattering on single molecules at a time. With the idea, of course, that because one can do this with X-ray pulses of femtosecond duration, one can actually detect really here ensemble information. So not an average, but single snapshots of the molecule in single states. Yeah, the trade-off, of course, is that one has to deal with quite a bad data quality here. So, of course, first, one has a randomly oriented molecule here at each time of scattering. And then second, one has extremely sparse images. So even with the brightest XFELs available right now, for like a typical small protein, one observes something like 10 to the 100, 10 to 100 photons per image. So really only, as you can see here in red, the positions of these very few photons on the detector. There is more, like background noise is quite substantial, low hit rate, so one typically only hits a molecule with 1% of the pulses, say. More than that, I'm going to sort of neglect these for now and focus on the first two here, so the random orientations and sparse images. And if we look at this from a more mathematical perspective, each image here is basically just a list of positions of photons in Fourier space, which are distributed according to the Fourier transform of the molecule. And so due to the geometry here, for each orientation corresponds to one sort of such Ewald sphere through the three-dimensional Fourier transform, and then the photons' positions sort of fall on this. And this also is sort of the idea what the sort of conventional approaches here are based on. So one tries to take the images, somehow guess the orientations, then one can puzzle this all together to a gigantic point cloud and then do the phase retrieval to get the actual electron density of the molecule. Problem is that this requires really way too many photons to be doable. So typically one says 1,000 per image, so at least 10 times more than are available. So this is sort of the vast majority of methods. There are some. I want to highlight one because it has been developed in the department I work in. So this is 3-photon correlation, where the idea is first to take the images, take a correlation function which is actually orientation independent, and then from this, in this case, a 3-point correlation function, actually one can get the electron density. This is really interesting because it shows that the limit here is as low as 3 photons per image. So actually quite a lot lower than what is available. Trade-off is here that one in this step from here to here, from here to here actually discards quite a lot of information. And so the Bayesian framework really offers best of both worlds here. And so that's what we try to apply here, of course. And so let's look at the likelihood here. So we have the probability of the images given the electron density. And this is then, of course, a product over all the independent images, then an integral over the random molecular orientation, then a Poisson distribution for the number of photons in the image, and then finally a product over all the single photon positions and the Fourier transform at that position. Now, to actually sample or maximize from this likelihood, what we've developed in collaboration with Russell Luke at the Math Institute here in Göttingen is what we call resolution annealed stochastic gradient descent, ascent actually. And so the idea is that we actually directly determine the atomistic positions in the molecule. So these are essentially just the Gaussian mixture model then. And we utilize a sort of a symmetry of this problem here. That is the Fourier convolution theorem. So because the images live in Fourier space, if we look at a smoothed version of the electron density, then the images that correspond to that are actually related to the original ones by multiplication with a Gaussian, or rather like deleting some of the photons. And so this we use by doing basically standard stochastic gradient ascent approach. But in each step, we consider not the sort of original images, but smoothed version of it, and compute the like posterior of a smooth electron density relative to the smoothed images. And so what this then looks like in practice is that we have a time-dependent smoothing parameter, which we let go to 0. So in the top row, you can see the actual atomistic positions here. The red arrows are the current gradient, and you can see how the gradient is really smoothed by this. And so this allows us to, in the beginning, make very large-scale updates, and then as this smoothing parameter decreases to 0, sort of more and more sort of fine-grained updates. So I hope this works over Zoom. So I have a video of this process. So you can see here the current smoothing parameter and actually the current Fourier shell correlation resolution. And you can see as this parameter goes to 0, the resolution also approaches something certainly near atomistic. Let's just watch this to the end. So you can see that we actually reach about 2 angstrom resolution here in the end. And so this was a test case on synthetic data for the lysozyme protein, 1,300 heavy atoms, which we have actually all determined here. 1 million images. What this comes out for this one is roughly like 80 photons per image, which you can see here. And so you can see on the left side the reference from the PDB, and on the right-hand side the reconstruction. What I find really exciting here is that this took only about this takes about 2 hours of computation on a single GPU. So the sampling problem is really quite well solved here, I would say. Hang on, I've done this. But of course, this was quite idealized data. So only coherent scattering, no background, and no other like nuisance parameters. In reality, of course, it's much more complex. So there's always going to be some other gas in the beamline. There's solvent, maybe evaporated, maybe sticking to the protein. Actually, the pulses fluctuate quite strongly in strength. And so more realistic representation of the images, this is still simulated, but like should be sort of qualitatively accurate, is this. So you can see here in red the signal photons, and in black actually the noise photons, and they really dominate clearly. And also you can see that only very few of the images actually contain data. And so those are the hits and the others are the misses. Problem is that if I like turn off the coloring, you cannot tell which is which. So this one actually has to take into account as a nuisance parameter. There's more, which are not as visible here. The standard approach to this hit and miss is just as for the orientations classification. So somehow sorting the hits from the misses, which again requires way more photons than are available here. And so we, of course, try to include this in the Bayesian framework. And you can see this here as this additional nuisance parameter. And what it comes out at is if one considers the beam profile to be a Gaussian in 2D, and then has a uniform prior for the sort of molecule position within that, it comes out to be a log uniform distribution for the relative intensity at the position of the molecule. And then, so this comes into that. So I don't really want to go into so much detail about the rest of it. So there's a lot of stuff included here. So the detector shape, and then the various kinds of scattering, including the background noise. And indeed, still from simulated images, but from, as you can see here, very much more realistic ones, we can still get quite a good structure here. So this is Crambine, again, from the PDB, simulated at 5% hit rate, in this case of 15 coherent photons per central hit. And so the resolution is, of course, a bit certainly not near atomistic here, but still you can see the overall structure is really quite well recovered here. Yeah, so this is that bit. I mentioned in the beginning the goal with this method is, of course, not structures, but ensembles. And so, yeah, what I want to sort of determine here is then a list of structures with weights. And the story is the same again. The conventional approach here is a classification, which only works then for much larger particles. And so, of course, we included this in the Bayes. And so in the likelihood, that only means that we have this additional weighted ensemble average. Yeah, let me show you a test case again. So this is chignolin, so a really small molecule, just to have a nice sort of relatively simple proof of principle test that is still relatively interesting. So this actually features in its simulated MD ensemble here, folded and unfolded states. Yeah, and then again from synthetic images, using a sort of older version of our software using MCMC sampling, we determined this ensemble you can see here. For comparison, I have now for each structure in this ensemble the closest frames from the MD trajectory that was used to generate this synthetic data. And you can see that sort of overall this matches relatively nicely. I want to point out that, so if we look at these two states which resemble the unfolded state, if we add them up, that's roughly 10%, which is actually pretty much exactly the unfolded fraction that we had in the MD trajectories. So the ensemble really was correctly determined here. Yeah, so actually already want to conclude here. So yeah, we have seen our Bayesian electron density determination method here, which circumvents the need for orientation determination. What I have not shown so far is that we actually have tested this on experimental data, not on proteins, because we, to our knowledge, don't have access to actual single protein data here. But what we can do to test this is actually take virus data, where this has been quite successfully applied previously, and just reduce the photon count sort of artificially. And indeed, from a 10,000 times, I think was it, downsampled data set, we actually can really still get the structure of this icosahedral virus and even see the internal structure. Yeah, and we've also seen how we can get structural ensembles here and how we actually can still get structures in a quite sort of extreme low hit rate and high noise regime. Yeah, and with that, I would like to thank the members of the research group at the Max Planck Institute here, particularly my supervisor Helmut, and yeah, we thank you for listening.
Thank you, Steffen. So with that, we'll open it up for questions. We have quite a bit of time for questions if anybody wants to. Yes.
There's a lot of integrals in computing your loss function, and I wonder if you have any comments on how you checked that your integration was working the way that you needed to in order to have a smooth evaluation.
Yeah, I mean, in the sense, just try to go to the sort of absolute maximum of sort of like base points for the numerical integrations there I could get, and until it was sort of sufficient, really. So, for instance, for this this integral over hit and miss, it actually turned out that using the right kind of quadrature rule, five base points suffice, which I find quite astounding still. Yeah, does that answer your question?
I guess so. I guess I'm looking for some sort of magic method to make sure that I'm doing my integrals right. And it sounds like it's one of those things that you really have to test.
No, I don't really
yourself.
know, other than, you know, if it works, then yeah. Something else I can say that the resolution I have in the lysozyme case of 1.9 angstrom, I think the limit from the number of base points there would be 1.6 angstrom I have used. If that gives you an idea of what, and that was like then 80,000 base points for the orientations.
Any other questions? Yes, Mark.
Yeah, so I'm not familiar with X-ray at all. So I was wondering, can you just give a quick description of like what the experiment looks like? Do you have to purify and put it in something? And also related is, why do you have access to so few photons? Why can't you just throw more photons at the sample?
I mean, I wish it was that easy. So experimental setup, yeah, I mean, of course, one needs the protein in some kind of purified form in solution. I have never actually done any of these experiments myself, I have to admit. So I'm really not really the right guy to ask there. But I mean, so supposing one has this purified thing, then there's injection methods, so electrospray, which uses some sort of relatively strong electric field to sort of relatively violently throw the stuff into the beamline in the hope that it sort of evaporates in actually sort of very fine droplets. More recently, they have gone to liquid sheet injection, where you have like a nozzle that actually spreads out a very thin film of liquid that's then micrometer thick. And that should really give you pretty good, actually in solution scattering then. And sorry, what was the other question? Oh, why one cannot increase the photon count? Yeah. Because it's just a big laser already. I mean, an X-ray free electron laser, I mean, is already 3 kilometers large as far as I know. Building a bigger one is not so easy. The alternative would be to increase the focus, but with X-ray optics, even that is tricky. You would also always sacrifice hit rate there. It's just that a single molecule has such a low sort of cross section compared to like a nanocrystal or so that you don't get much photons there.
That makes sense. Thank you.
In your Chignoline example, you had 3 states as your prior. How did you determine that?
3 states as the prior.
Yeah, three. You had a folded, unfolded, and an intermediate, I think, right?
Yeah, sort of. Chignoline does have these 3 states. This is not something we have at all included as a prior.
Okay.
So the only prior information really is that I tried this with an ensemble of 6 structures and their weights. So I have asked myself if I can actually see this distinction between this folded and the misfolded state, but I think the resolution is just not there that sort of I can make a sort of identification of these recovered states here.
Yes.
It seems like the examples were all of small proteins and small molecules. Is there an estimate for how large of a molecule could be used on this?
The upper limit is as large as you want. It actually gets easier the larger the particle is because you get more photons per image. So I have done some tests on different sizes. Hang on. Yeah, so here I have, this is the noise-free case, but so I have here 3 separate proteins. The largest one is the lysozyme we have seen. And actually you can see the crambine, this is 46 residues, whereas this is like more, a few hundreds. And you can see that if we look at how many images are required to reach a given resolution for the smallest one, it's actually by far the highest. And that is just because the images there contain fewer photons. And if there's all background noise and all that stuff, then this effect is much more clear. And I mean, in the end, that's really the reason why this has so far experimentally been applied to viruses, right? Like much larger stuff where you get millions of photons per image.
Can I have a question about, like, you have included so many physical effects in your likelihood calculation. Have you done any like ablation study to understand which effect is more important and which one is like ignorable? Right.
Not really. I mean, in the end, it's relatively obvious that sort of the ones I've included, the polarization is so weak that it's sort of not necessary, but it's also relative sort of basically for free because it's not a nuisance parameter. And of the sort of background noise, I mean, you really have to get that distribution correct. Otherwise, everything breaks down and yeah, you will not get a reasonable structure. Yeah. So the answer is all of them are necessary. And if you delete anyone except this polarization one, it breaks down.
Thanks.
Any other questions?
Thank you, Steffen.